Okay, welcome everyone to this continuation of Lie theory. And we are finally at my favorite part of Lie theory. I feel like I say that every time. But anyway, representations of Lie algebras or Lie groups are roughly the same because Lie groups and Lie algebras are roughly the same. And yeah, these are really important. So it turns out that most of the time, groups or objects like that, they usually turn up in the wild via their actions, via their representations, and not as abstract objects. And it's the same here. So a lot of quantum physics, for example, is based on representations of Lie groups, which was kind of historically interesting. It was kind of developed by physicists without knowing that the mathematicians have done something similar. But anyway, it's roughly the story. We are talking about the 1920s here. I'll give you some historical details. Well, not many, but some historical details in this video. Yeah. So representation of Lie groups, a really cool topic. Works extremely well. It's ridiculous how good that actually works. It's really good. And eventually, you don't even need to know what a Lie group is anymore. You can just do it combinatorially. It's kind of very interesting. Or even geometrically. Yeah, it's very interesting. So why representations? So here I have a representation, or a group action in the wild. Right? A group action is literally just a symmetry, if you want. I take here a very simple group. Z mods 3Z, why not? And it acts on this street sign because this street sign has a threefold symmetry, the roundabout here, right? It would send that guy to itself. Oh, great. So that's one. It would send that guy to that guy. So it rotates G and then, well, H. So this is like, if you want 1, G times G is H, and so on, right? So these are the three elements for Z mod 3. And it acts by rotation because it's a rotation thing. And I illustrate the symmetry here by breaking it, by just mark, right, this guy has a symmetry. And the action simply means if I rotate it, you can't see a difference. So I mark it, so it's not symmetric anymore, and now you can see the action. So that's a group in the wild, right? It acts on some object. This is not a Lie group. Oh, this is not a nice Lie group, just forget it. But as an example, that's what the abstract groups, right? They appear in the wild via actions. And this really just means they appear in the wild by some symmetry, some space. The symmetry doesn't need to be faithfully represented like here. It could be whatever, a bigger group acting on that thing in the same way, and a lot of elements just lose their structure and you can't see the difference anymore. But it's some form of symmetry. So a representation is some form of a symmetry. And it's more precisely everyone's favorite way to see symmetries, namely as a linear thing, because linear algebra is just too good and everyone loves linear algebra. I think I have said that 1,000,005 times. If you don't like linear algebra, I'm sorry. You should. Linear algebra is good. Linear algebra is really good. Okay, so symmetry, linearize, representation. That's what it is, right? In a vector space, we can compute things. Great, we like that. Yeah, and the slogan is literally, again, groups do not appear in the wild as abstract objects. They simply don't. I mean, sure, you can cook up examples, but most of the time they come via actions. And the representation is just a linearization of that action. And whether you want to call it an action or a symmetry is mostly a matter of taste. That's literally what it is. Huh? And just to make it completely clear, I play my example here. Right? So here's the same action from before, but now I want to do it on the vector space. So I think of my three marked street signs as vectors in 3 space. Yeah. So this is just a 3-dimensional vector space. And G, for example, sends that one to that one, sends that one to that one, it sends that one to that one. So it's that matrix, right? It sends this guy to that guy, so that matrix. Sends that guy to that guy, so this column. It sends that guy to that guy, so that column. So now G is a matrix. Yeah? It's not just an abstract thing, but it's a matrix. That's the whole point of a representation. I just rename the parts of my symmetry into vectors and see what the actions do, and I get a matrix. And more formally, there is a map called a representation, right? Each element you associate a matrix. That's a representation. Each element gives a matrix. It's a representation. Not in an arbitrary way, but essentially the group structure is rather repeated in the matrices. Those are not abstract objects anymore. They're literally matrices now. Yeah. So the group law is translated into matrix multiplication. Why is that fantastic? That is fantastic because now it's a matrix and you can play whatever. Diagonalization tricks, you can play eigenvalue tricks, you can play determinant tricks, trace tricks, linear algebra tricks. And that's not just abstract, it's just linear algebra tricks. And linear algebra tricks are really good. It's essentially the only thing we understand are linear algebra tricks. Very sad state of the arts, by the way, but it's kind of the only thing we ever understand. Linear algebra tricks. Okay, hopefully this is clear. It's literally just groups are symmetries. Lie groups are therefore also symmetries. But abstractly they're difficult, so you just realize them in matrices and hope for the best. And yeah, I wouldn't have this video if the hope for the best wouldn't work, because if the hope for the best doesn't work, then there wouldn't be representation theory and it would have collapsed 100 whatever years ago. So it does work. So hope for the best does work, yeah. And the standard examples, so here are, this is essentially the picture. So a Lie group acts on a sphere, for example, rotations, and the Lie algebra will act on a tangent. Now that's literally what is going to happen, but in this video, we only have Lie groups. So matrix groups act on column vectors by definition. This is usually called the defining representation. And if you have 2x2 matrices, they act on a two-dimensional space as matrices. Now, that's the defining representation. So matrices are already, matrix groups are just better than general groups. That's just what it is. Yeah. Rotations act as rotations. Permutations are perfectly good linear actions because they are literally matrices. So this, for example, is a permutation matrix. Perfectly good linear matrix. Cool. Story time. Story time is always good. So here you see the first ever published character table, I think, from Frobenius. For some reasons, it was the character table of A4, or as everyone knows, the symmetry group of the tetraeder, as Frobenius writes here. So it's Frobenius writes in German. That's just what it is. But anyway, this is a character table, and essentially this is a representation of the group A4, which is a very, very efficient representation of the group A4, because essentially it's just 4x4 numbers, 16 numbers, as a representation of the group. Anyway, so the history goes as follows, roughly. So people, Frobenius in particular, was really interested in those characters, which have been around way before representations, and were quite mysterious at that point, and Frobenius studied it more carefully, so they're related to Fourier transform and all of that, and Frobenius studied them very carefully and came up with representation theory, essentially. And by Frobenius, I merely mean Frobenius and friends, because science is a group activity, and yeah, sometimes people are just, well, we associate big names to whatever, right? So our hero stories, we like heroes, we just associate a name to it, but in reality it was more like a big group of what. This roughly was the 1890 something. A bit hard to say, right? These ideas have been around a bit earlier before the published date, but let's say 18, oh my goodness, it's a long time ago. Let's say it is a long time ago. And essentially the idea is to do the representation trick. And for finite groups, you're even luckier. You can turn it not just into matrices, but you can turn it literally into numbers. Yeah, literally into numbers. You don't need to know finite group representation theory. I just tell you about it now. Or all you need to know is kind of this historical, we won't see it again. All we need to know is this historical background. So the whole idea on why this is so important, that characters, the numerical shadows of groups were then used in finite group theory, in the abstract theory of finite groups, and then characters of groups just appear everywhere in modern mathematics and beyond, like in chemistry, when you have a symmetry of a molecule, something like that. And in hindsight, literally finite group representations or symmetries, finite symmetries, are combinatorial objects. That's the whole point. So these numbers are combinatorial objects, if you want. Yeah, that's the whole point. Cool. So people started with finite groups because finite groups are finite. Sounds very easy, but actually Lie groups are easier. It's kind of strange, but it came up later. Story time. Let's go down. Story time. Lie groups. And roughly in the 1920s, as I said, in parallel to quantum mechanics, essentially. So Weil was a very big name in mathematics, did a lot of things, representation theory, invariant theory, physics, mass physics. So Weil did a lot. And again, it's Weil and friends, really. Yeah, our hero stories. I just pick up one hero, but in reality, there are many, many heroes. And yeah, so Lie groups, and essentially very important, it's kind of a generalization of Fourier analysis. And Fourier analysis is one of the few tricks that actually work. So people like that a lot. And the key difference, before I tell you a little bit about the story here, the key difference is that Lie group representations, which we are going to study, are geometric. Finite group representations are combinatorial objects. Lie group representations are geometric objects. Right? Slightly different. But sounds fancy. It's geometric. Sounds fancy. Combinatoric sounds easier, but geometric is actually easy. So the geometry is really easy, and you can understand it as a whole package. And for finite groups, it's more like you can understand every finite group separately because they're kind of more discrete objects. They're a bit more random, and these are a bit more ordered, if you want. And the book, which I would not recommend to read, because Roger Howe actually said it's wonderful and terrible at the same time. But essentially, the book here, the breakthrough book, is, while again, the classical groups. By that, you just say matrix groups, essentially. Yeah. So Lie groups, a little bit later, representation theory of Lie groups in the 1920s, in parallel with quantum mechanics, because essentially quantum mechanics is all about representations of Lie groups. The standard model of particle physics is like Lie group representation theory in some way or form. Anyway, this was mostly a story time lecture. Hopefully it was reasonably enjoyable. Next time I do a little bit of story time about representations of Lie algebras. And then the best way, I think, how to explain what's going on is we just look at an example and take it from there. Anyway, I hope you enjoyed this video, and I also hope to see you next time.